Welcome everybody to our ninth webinar series, and today it's about what's wrong with my control system, control performance monitoring at water resource recovery facilities. I'm very proud of my development team, and today Ivan Miletic, our data analytics leader, and Masa Sadekasai, she is our control expert, will present some of their findings on controller performance monitoring. Right, so that's quite a challenge, and you will see that they really did a fantastic job coming up with solutions. So I would like to start with, if I get that out of the way, yeah. I would like to start with some context, yeah. So just to explain a little bit more why we do that, and also how today's presentation fits into our development work. So in control's vision or mission, you could also say, is to make process control work. Yeah. So that's a bold statement and task, but we do that by actually combining all kinds of different skill sets and traits, and we try to combine that and encapsulate that in software. Yeah. So there are different parts to a control system, and I just want to briefly go through these four main parts. On sensors, it's not discussed today, so there are other webinars we gave and will give on sensors. Basically, what you need is accurate and complete data, and that is essential for whatever engineering work you do, but especially in control. And of course, we want to automate that. So our monitoring control platform, we call Ops Control, supports sensor maintenance. Right, so that is organizing, cleaning, for example, changing chemicals, and at the same time make sure you get the best possible data out. Yeah. In terms of processes, process monitoring, we use a lot augmented data, right? So augmented data is basically creating soft sensors and allow you in-depth analysis, and what have not measured, we model, right? So we augment, so we complement the data set so that we can actually look into things you typically couldn't. Yeah. Equipment, that's not something we released yet, but we are working hard on providing solutions for that as well. Basically, our goal there is to make equipment talk. Yeah. Okay, so let's look into controller performance monitoring. So I would say in our industry, we have quite a deep understanding of all the involved processes and equipment. So we have experts, mechanical engineers, process engineers, instrumentation experts, of course, control engineers, and so on. So we have that out there, and we have a good understanding, but still we so often see that we end up with poor control performance. So why is that? Right. So and a lot of people now talk about artificial intelligence and machine learning and model-based predictive control and so on. And we love that stuff, right? So not that we are against it, but if I look just through a couple of projects I looked into, artificial intelligence, there was one study saying, oh, we should actually set blowers on timers, right? So that's going back into the 60s, right? So that's not improving, that is just creating a mess, right? And artificial intelligence or machine learning, whatever they used, they looked into that, realized there is a very regular pattern, and said, well, then we put it on a timer. Right, so really bad solution, and nobody at the right set of mind would actually recommend that. But well, that filter doesn't exist for Feed-forward control, again, so that there will be solutions where that makes sense, but just understand your equipment and your process, right? So for example, if a valve is already open, right? So there is no controller in the world able to provide more air, right? So at least not for that specific control, right? So if the valve is open, it's open. Same with DO. So that's an equipment limitation. So if DO is already at 2 milligram per liter, then more air is not helping, right? So you have to understand what are the limitations of process and equipment to actually make it work, right? So sometimes you hear new control formulations like floating point, and that's just a very slow integral controller, right? So that's nothing new and actually would not perform better than a classic PI controller, right? So that means you have to understand the equipment, mechanical engineering, you have to understand the process engineers, and you have to understand the logic, so control engineers need to be involved as well. Okay, so how to make it work, right? So what we try to do is really understanding what is limiting the performance. And we do that by providing understandable metrics, right? So that all the experts involved can understand that. Very important is visualization, right? So if you cannot visualize that, you are not able to bring it down to the essentials, right? And it's very, very important to make sure that you get that message out and that you have something you can discuss with the other experts, right? So at the very, very end, you pick the right control solution, right? And again, so we love all the data-driven modeling. So there is not a single project we do without some level of data-driven modeling, not a single project, right? So we do that all the time. We combine mechanistic and data-driven models and just make sure we find the best solution for our clients. Yeah. So my message here is let's be smart ourselves and do proper engineering work. Okay, with that, I hand back over to Ivan and Masa. Enjoy.
Okay, can everyone see my my slides? I hope they can. The main thing that we're going to talk about today is how to assess the performance of controllers in the context of wastewater treatment plants. Okay, and we're going to show you some work that we've done over the last while to develop these techniques and to bring them to a useful state in the form of some software that we've developed. So what we have here is basically a screen capture from our ops control software platform, and we're hoping that you realize that all of the techniques and the topics and the algorithms and the methodology and the workflows that we're going to discuss in these slides, including the examples, are already developed and they're encapsulated in this software. So this is available for people to use for practical application in a wastewater plant. Okay. So the outline of the presentation, or what you're going to see today, is basically a brief introduction on how you can first diagnose, detect, and then diagnose problems in control loops. And the focus here is on controllers. But as Live was saying, you should also keep in mind that that sensors also need maintenance, and that that this is a topic in deep enough on its own that that we want to keep that sort of as a separate seminar, but that we do include this as part of our assessment, because sensors certainly are part of control loops. Okay, so we're going to show you some examples on control performance monitoring, and especially the diagnostics piece of this. It's one thing to be able to detect the problem and identify that a problem exists, but it's another thing to be able to understand how to fix the problem. Okay, and then we're going to see we're going to open the seminar for discussions and questions, so you guys can provide us some feedback on all of this. Okay. All right, so control system fault detection. Realize that the slides that I'm going to show in this section apply for general fault detection methodologies. But in the case of a control loop, you're looking at these basic components in a control loop. You're looking at the process itself, which is basically the plant where the controller is installed, and that, in my mind, includes the equipment that the biochemical process is sort of evolving in, and it includes sensors that measure certain variables on the process, and then various control algorithms. In this case, we're focusing on a PID algorithm in this presentation, the proportional integral derivative controller. So these algorithms typically compare the measured value that comes from a sensor, and the algorithm is then applied, and a manipulated variable of some kind, a control action, is calculated and then applied in a either at a final control element or in a control cascade to affect a change in the process. And this continues on over time, and it acts repeatedly over and over again as new data are made available. Okay, so what you want to then be able to do is say that that the controller that you have in your plant, the way you've tuned it, the way you've connected it to the data that the control algorithm needs, that this controller is able to meet the its basic goal, which is to drive the controlled variable to its set point. Okay, and it does this through the application of these mathematical forms. So we want to see how well these algorithms are performing relative to the data that are available, and that's the focus of this presentation. Okay, so these fault detection methods for control performance monitoring are you can think of them like as any other fault detection method. To detect the fault, the first thing you need is some kind of a basis of comparison. So if you want to detect that something bad or abnormal has happened, you first need to understand what good is. And in this case, and in many cases, the idea is to apply a benchmark of some kind. The benchmark can be model-based. It could be laboratory measurements. For example, in the case of sensors, you might say that you could apply control theory, or you might have a control person, a control expert that can give you their opinion on how the controller should operate. And then you can benchmark against that and see how well your controller is performing relative to that benchmark. Okay, so the idea then here, for us at least, is to establish a theoretical benchmark, which we do, and then we use that benchmark to compare the performance of a controller we're analyzing, and to provide an assessment. And these are, and as you can imagine, these are data-driven techniques that do the analysis for the measured values that are available from these control loops. All right, so that may be fine enough, but you should realize when you're looking at these kinds of systems and assessing their performance, is that the algorithms and the math are really never enough. And this is true in most fault detection applications, not just for control performance. The idea here is to detect and diagnose the fault. For sure, that's true, but you also want to be able to present this to a user in a useful way so that the user can do something about it. So the user knows that a fault has occurred, knows that the fault has occurred in early enough, and then give the user some suggestions on actions to take. Okay, and in the case of what we do, we're looking at various modeling methods, one of which you're going to hear about in these slides to establish these benchmarks. Okay. Now, the methods themselves, how do you actually do the fault detection once you have this benchmark? And you're going to see how we do the benchmark in a few slides from now. But once you have this benchmark, what do you do about that? How do you actually detect these faults? Okay. One way to do that is to apply a control chart model to the streams of data that are available from this process you're trying to monitor. Okay, in this case, the process is a control system, but it could be some other part of your plant. It could be a chemical reactor, a biochemical reactor. It could be anything that you have reliable data for. So how does this work? Basically, what you do is you take your you take the data that you get from the process. You perform calculations on the data to come up with some kind of a metric that might be useful and that indicates a performance of your system. So once you have that, you can put that onto a chart that looks similar like this, and you can plot the metric over time, and then compare the metric to various control limits. And you can set these statistically or theoretically or based on, like I said, an expert opinion. You can set the limits, and then if the metric exceeds these limits, either high or low, you would infer that a problem is occurring. Okay, so the trick here then is for control performance is to come up with the appropriate metric and then to chart the metric like this, and then to do decision support using software to help a user of these techniques affect the change in the plant that's beneficial. Okay, so one of the messages that we want to get across with these slides is that the workflows that are needed to support this, especially for non-expert users, can be quite complicated. And it's quite the trick to get them simple enough that pretty much anybody can use them, but also to make them comprehensive enough in terms of scope and what they can do with the mathematical models that are being used, that they're very sensitive to faults. All right, so. What we're looking for here then is to provide workflows to support a control system performance monitoring, also for sensor data quality and for any other process quality assessments. There's a whole long list of items you can put underneath these workflows, but the ones we're focusing on here is for control performance monitoring, and you're going to see what some of these look like in a few slides. Okay. All right. So. If we're going to focus on control performance monitoring, so remember the process provides data through a sensor. The sensor sends that to an algorithm like a PID algorithm, and then this algorithm calculates a control action that is applied in the plant, and the whole thing is repeated. This feedback loop. So if you're going to monitor this, and you're going to focus on the control system part, the circled part, what you'd like to be able to do is say that the way you set up the controller is good. hopefully you would like to be able to say that you have good operation of your controllers in your plant, and that everything is operating as well as it can. But you'd also like to be able to say that the data that the control algorithm is using, that these data are also in good order, and that the control algorithm can actually make use of the data in an appropriate way. So if you're going to do monitoring of a control system, in this case a PID controller, you want to monitor the operation of the controller. It's providing the control action, but also you want to monitor the quality of the data that are going into the algorithm. And that's what we're talking about here today. So you're going to see some examples of how to do those two main tasks. And once the assessment has been done, we'd like to be able to show some suggestions to a user on how to modify the settings for the controller to improve the performance. And that's a tuning question that we're gonna talk about in the examples. Okay. All right. So some of the metrics that you might see in these sorts of applications when you're talking about the quality and the performance of control systems in general, you might look at metrics that are based on these distance measures. How different is the measured value from a target or from a mean? And those are these RMSE, the root mean squared error, the integral error. They're basically different functions of this error that you can calculate that the PID loop or the PID controller is operating on to move the controlled variable to its set point. Okay, and you can also look at other combinations of these variables, various statistical measures of these things, but also realize that one very important metric that kind of gets overlooked in a lot of papers that you see on these topics is bound checking, and checking that the controller is actually able to perform the control moves that it's designed to provide. Okay, so and this for us falls into the framework of checking the quality of the data that are available. If the data are showing an indication that the controller is sitting on bounds, then it becomes a question of whether how well you can evaluate the performance of this algorithm, because the algorithm really can't do much with the controller sort of stuck on a bound. Okay, so these are the kinds of things that we're looking at. Now, in addition to that, the idea of the quality of the data. So realize that the algorithm requires a fair bit of data, and that the data that we're getting here, that we're talking about, and we're focusing on closed loop data that we get from a typical database. So we're not talking about some kind of a plant trial or any kind of fancy tests that we have to do in a plant. We're doing this based on data that we can get from a typical control system that of the kind that you can find pretty much in any plant. Okay, and this is on existing data that are normally logged. So what we want to do then is check the data length to make sure we have a sufficient number of data points to provide the information that we're after. Make sure that outliers and missing values and these sorts of things are taken care of in the data set. And then we look at bound violations and consider how often the controlled variable or the manipulated variable, sorry, is sitting on its bounds. And then we look at any sort of statistical variations and how often the set points and the controlled variables are actually allowed to move. And the reason for this is that allowing these variables to move in the plant is actually the richest source of information that we have for these systems. So we have to sort of go through the data set, prune the data set, and then provide an assessment of performance by looking at these various features. And when I'm mentioning this, realize that this has been done. This is being done automatically with no human interactions whatsoever through various algorithms that we have to do the data preparation for the performance assessment. Okay, so all of these checks and these kinds of tests on the data, that's a part and parcel of the application of this. Okay, and once we have assessed performance for a controller, what we want to do then is be able to provide a set of values that can tell you how to set up your controller for better performance. Okay, and typically what that means for a PID controller is to set these circled parameters, the KC, tau I, tau D values that will impact the performance of how the controller is calculating the MV, the manipulated variable, to improve performance. And this is what you see on that plot on the right hand side of the screen here, is that, and this comes from a full scale a wastewater treatment plant. You can look at the controller, which is in blue, which is the CV, and the set point, which is in red. Before tuning, the blue controlled variable has a lot of trouble, especially in those during those dynamic moves in the plant set point. It has trouble in tracking the set point. Okay, and then after tuning, you notice that the set point and the controlled variable are basically right on top of each other, and that's what that top plot shows you. And then what you also see is that the error is drastically reduced between basically the difference between the set point and the controlled variable. Okay, so that's what we're after with this. That's kind of the goal of these tuning exercises that these software algorithms provide. But realize that the main idea here is that these are done in an automated fashion without any expert knowledge. So the data are assessed, and then tuning is provided. Tuning suggestions are provided for the user that can provide this kind of change in control performance. Okay. So our preferred tuning method is to look at the application of an automated tuning framework. Basically, the steps are that we fit a small model of the plant. This is a data-driven model, and then we apply the model in very quick. By quick, I mean it takes a few seconds to do this. Simulations that can be used to establish the performance of how a PID controller could operate in this situation, in a situation where it's installed, and we use that as the benchmark. So what we do then is we compare the performance of the controller that's actually in the plant to the one that we simulate with our tuning suggestions, and then we offer an idea to the user of the software how they can achieve that performance by adjusting the tuning in their plant to meet this benchmark that we've established. Okay, and this is done in an automated fashion, like I said. Okay, so how is this done? This is a little bit more detail. So remember, the goal here is to set those KC, tau I, tau D parameters, one for each term in the PID controller. And what we want to do then is set them so that the controller can better track the set point. Okay, so we're targeting here a PID controller performance, but this can be done for various controller forms. We fit a plant model, first order plus dead time model, using a data-driven method with impulse response methodology to do that. Then we apply the simulation, and then we generate estimated tuning parameters based on that simulation, and then we allow the user to apply them in the plant with two-way communication with our software. Okay, so the main thing here is that the assessment of the performance is done, including a look at how well the data themselves are performing, if the data have enough information in them, and then the algorithms provide suggestions on the tuning parameters, or they give an indication that there's something wrong in addition to the controller. For example, maybe bounds need to be checked and assessed so that the controller actually has room to move. Okay, so I guess now we're going to turn this over to Masa, and she's going to discuss some examples of how these techniques can be applied in various scenarios, starting with the controllers on for a full-scale wastewater treatment plant in Europe. Okay, thank you.
So can you see my screen?
Yeah, we can, I think.
Okay, so I'm going to show you here some examples that actually demonstrate the capability of our software ops control in finding actually the source of the problem of a feedback loop that is performing poorly, and the ability of our software in suggesting some solutions to solve these types of problems that happen in feedback control loops. So the first example is actually an example that the problem or what is limiting the performance of the feedback loop is not the tuning of the controller, and the reason is some equipment and process limitations that prevent the controller from tracking the set point closely. This is a screen of the interface of ops control software. So the control loop that we are looking at is a mixed liquor recycle controller. This is a full-scale plant. So we installed our software for this plant, and it's installed there. Our software is receiving the data in an online manner in real time, and we are actually storing the data in the database. So we are able to analyze the data or evaluate the data, or do whatever we want to do to evaluate the feedback loop. So this is one of the loops for that full-scale plant. One of the features of the software is that it can shows the value in real time, which means that the control variable, manipulated variable, and the set point variable values are updating over time. So the control loop that you can see here, those values for the those values with the units of gram per cubic meter, they will be updated over time and regularly. The graph on the bottom shows how the control variable track the set point. So the blue line is the control variable, and the green line is the set point. So the set point is actually fixed at 1. What we can see is that the control variable is not able to follow the set point nicely, and in most of the time there is the control variable is far away from the set point. So our ops control software can tell us why this is happening, and can actually tell us if retuning the controller can solve this problem, or we should try to find the solution somewhere outside of the controller. This slide shows the diagnostic check of our software. So it actually gives you an idea how is the suitability or the suitability of data that are coming into our algorithm. So what you can see here is that the software does not evaluate the performance of the controller, and it does not suggest retuning the controller. And that's because there are some problems with MV and the set point. So the what the diagnostic check suggests is that we need to look at the MV, and that bars, those diagnostic checks, shows that we are actually hitting the lower bounds for that manipulated variable, and that is what is limiting the performance of our loop. The next thing is that there is problem with there is insufficient information on the set point, so it means that there is not enough variation. Now, all of these conditions, all of these checks together suggest that it's not a good idea to change the tuning of the controller as the first step, and it's better to like look at the source of the problem and then try to solve it that way. So the source of the problem here is hitting the bound by the manipulated variable. So in that case, we are not, even the best tuned controller cannot help us to improve the performance of the closed loop. Another example is that one that shows that retuning the controller actually can help to improve the performance of the closed loop, and our software or ops control software is able to suggest the appropriate tuning for the controller in an online automated way. Yeah. Yeah. So this example is actually implemented in Symbo environment. Actually, Symbo environment is a very good place for us, at least for testing our ops control for our software, because we are able to implement different models there, with different levels of difficulty or complexity, and test how well our software can work when it faces different types of problems. Yeah, the example here actually has two basins and one aeration system. So the basins, both basins are in Cascade framework and have three control loops. So the first one is ammonia, then the middle control loop is dissolved oxygen, and the last one is the air, Q air. The aeration system has a most open valve, which is followed by a pressure controller. So as I mentioned, for that full escape plan, here again, MV, CV, and SP values are collected in real time, and they are stored in our database as time series. Yeah. So in this case, we need to analyze the whole cascade together. So our strategy to analyze the cascade is that we will first, or initially, we will look at the control loop that is further down into the cascade, and then we will move to the controllers that are in other loops. So here, the inner controller is actually the Q air, but when we look at it, we can see that it's not in an alarming condition. So we do not need to retune that controller. So the next one is the dissolved oxygen one, which is in alarming condition. It means it's also shows by the red color. That red color in our software actually shows that the control loop is in alarming condition and something has to be done to solve that problem. So when we look at the diagnostic checks, we can see that MV, CV, and set points are all in good conditions. So all of them seems to be okay. So then we need to look at that metric. That CPI here is actually the metric. That metric is running in real time, and then actually compares the performance of the current controller to the to a well-tuned controller, which is our benchmark actually. So the CPI is actually shows the or compares the performance of the current controller relative to our benchmark controller. And what we can see here is that our software suggests that the controller tuning is too loose, and the software suggests that the tuning change needed for this control loop. So this slide shows how our software does actually, how our software advises for a new tuning sets for the controller. You can see that the old parameters of the controller are shown in blue, and our software suggestions are shown in green. So you can see that our algorithm advises for a more aggressive controller. It suggests that the controller should work more aggressively, which is a correct direction, because CPI actually in previous slide says that or indicates that the controller was tuned too loose or too slow. So the user has the ability to push that apply new setting button. When the user pushes that button, the new settings of the controller will be sent into the DCS system, and the plant will be running with that with the new controller parameters. And if the user has some expert knowledge and wants to play around with the values, our software has this option. They can make it a little bit more aggressive or a little bit more loose if they want, and see the results, and then confirm the results and send them to the DCS system. Yeah. So this slide actually shows that how that automated online tuning way that we have in ops control can help us to improve the performance of the DO loop. So you can see that with the initial tuning, the DO is in alarming condition, and the bottom graph shows that we are far away from the set point. So actually the CV, the blue line, is not able to follow the set point. So after after we apply the new settings, you can see that the CV is actually on top of the set point. So it's hard to see that dotted green line here, because actually that blue line is on top of it. The color actually shows that the controller is no longer in alarming condition, and it moved from alarming condition to a warning condition. And then if we wait for a little bit of more time, the controller status will change to good. That's because we need a little bit of time to get rid of those poor performances, and we need to get rid of that averaging effect and those types of calculations that we do in our software. But after a while, we can see that the controller color has changed to green. And we can see that actually the CV can follow the set point nicely. And what is interesting here is that even the manipulated variable is not aggressive. So it means that even after the tuning and we applied a more aggressive controller, the manipulated variable is still smooth, and it shows that the manipulated variable is in good condition. So it means that the tuning, what the auto-tuned PI controller of ops control suggested actually helped improve the performance of the loop. Yeah. This one shows how our CPI, how our metric works. That metric, as I mentioned before, actually compares the performance of our current controller relative to a well-tuned or benchmark PI controller. The idea or the goal is to make that index be as close as possible to 1. When it's close to 1, it means that our controller is working closely to that benchmark controller. And when it is bigger than 1 or it's much smaller than 1, they are both indications that something is wrong. When it is much greater than 1, for example, it suggests that the controller is too loose. That was the case for the dual controller. When it is too small, it means that the controller is too aggressive. maybe we need to retune the controller and like make it more reasonable. So this graph actually shows how that metric changed over time, because we calculated actually online. We run it with real data online, and then you can see that when it is close to that red limit, it means that we are far from the desired performance. And when it gets close to that yellow lines, and when it gets closer to 1, it means that the controller is working in the way that we want it to work. The next example again is an example that process constraints are limiting the performance of the control loop. This example is actually an ammonia controller. And if we want to analyze the cascade, we can see that after applying those new settings for the PI controller, both DO and Q air now are in good conditions, so we can actually evaluate and assess the performance of the ammonia controller, which is like the most author controller in our cascade form. And we can see that again, because the ammonia controller hits the MV bounds, and because there is not enough variation for the set point, or software does not suggest retuning of the controller. It actually does not evaluate the performance of the current controller and does not suggest any new settings for the controller, because the problem is coming another source. It's not coming from the controller. Yeah, the conclusion here is that we should always look at the controllers like together with other constraints or limitations that may affect the performance of our loop. So it's not a good idea to like start changing the controller parameters or adjusting the controller parameters as soon as we realize that something is wrong with the performance of the control loop. It should always we should always look at it together, together with like looking at other constraints or other things that may limit our performance, and then try to find out the source of the problem, and then take an appropriate action according to the source of the problem. And also ops control software is actually able to give us some suggestions in that regard, and tell us what's actually wrong with that loop, and can tell us if retuning the controller is a good option for that control loop, or it doesn't worse to change the tuning of the controller. And our ops control software can, if the problem is coming from tuning, our software is able to do the retuning in an online automated way to improve the performance. Yeah.
Thanks, Maza. Great presentation. So there we already have a couple of questions. So there were